Hello, my name's Jude Wells and I'm presenting my research Chainsaw, which is a supervised machine learning approach for protein domain prediction on AlphaFold structures. So a quick introduction to protein domains. So we consider protein domains from the structural perspective, where these are self-stabilizing units, and the images here really illustrate what we are talking about when we talk about the CATH task of protein domain prediction, where we take this 3D structure and want to decompose it into these separate domain units. So why is this an important problem? Well, in the last few years, AlphaFold has released approximately 200 million predicted protein structures, and we need to organize this data to be able to infer homology, evolutionary relationships, and protein function. And also, equally importantly, in order to discover if there's any truly novel structures in this giant new database, we need to first take this step of decomposing these protein chains into their individual domains. So quickly we'll talk about how we represent the domain assignments. So we represent the protein domain assignments as a L by L matrix where entry ij in that matrix is 1 if those residues I and j are in the same domain. So we refer to this as an adjacency matrix, but you could also call it a co-membership matrix. In cases where the domains are contiguous, such as that on the left, that gives rise to this block diagonal structure. And in cases where you have non-contiguous domains, you get this off-diagonal pattern as represented by the non-contiguous domain in magenta on the right. And so we train the neural network to directly predict this adjacency matrix. Next, we'll talk briefly about the input feature representations. So there's 3 components that we represent the structure with. There's the inter-residue distance matrix, and there's the secondary structure co-membership, which indicates if residues are in the same secondary structure components. And finally, we have the secondary structure boundary matrix, which markates the start and end of secondary structure components. We have separate matrices for helices and strands, and next we'll talk about the network architecture. So Chainsaw is a 2D to 2D convolutional neural network with a ResNet style architecture, which is based on TR Rosetta, which is a model that was originally made for protein structure prediction. And we train the model to directly predict the adjacency matrix A. When we get that output of the neural network, we have this probabilistic predicted soft adjacency matrix that represents the probabilities that any pair of residues are in the same domain, and we need to resolve this uncertainty into a final domain assignment. And we achieve this using a greedy algorithm that iteratively assigns each residue to a new or existing domain, and we evaluate whether that increases the probability or the likelihood of that final assignment given the output of the neural network. And you can see from these images here that these feature representations are able to recover some quite complex domain assignments with lots of discontinuous domains. We also find that the likelihood score of the final assignment given the output of the neural network works as a reasonable uncertainty score that is quite highly correlated with the model accuracy. So to show some results, we benchmarked against other leading methods for domain prediction, and we showed that Chainsaw outperformed all of these methods even when predicting on a novel test set which is non-redundant in the sense that there is no domain in the test set that shares a topology or fold with any domain in the training data, and we used the CATH domain assignments to establish our ground truth. We also evaluated Chainsaw on AlphaFold structures and did a visual inspection of the results, and here we highlight just a couple of differences between Chainsaw and the next best predictor, which is Unidoc. So one of the limitations of Unidoc is that it is not able to predict residues as being non-domain. So looking at the comparison of images on the left here, you can see that Unidoc assigns the entire protein sequence to one domain, even though it contains a lot of these long regions of disordered amino acids that don't contain any secondary structure that seem to have been quite poorly modelled by AlphaFold. Contrastingly, Chainsaw is able to assign these residues as non-domain and pick out the components which are well folded by AlphaFold and consider these as separate domains. Secondly, if we look at the comparison on the right, this shows another advantage that Chainsaw has over Unidoc. So Unidoc works by clustering secondary structure components in order to generate domain assignments. And the limitation of this approach is that it's unable to predict domain boundaries within secondary structure components. So the Chainsaw prediction, you can see from the red circle here, that Chainsaw is able to create a domain boundary in the middle of this alpha helix, resulting in a successful domain parsing, whereas Unidoc is unable to do this and as such has a less clean parsing of this particular AlphaFold structure. That's all from me. Thanks for watching my presentation, and I hope to see some of you at the conference. Thank you.